Hello everyone. Now, in the last session, we have started our unit 3, that is the geostationary orbit, right? And in which we have discussed about the introduction of geostationary and about antenna look angles. Now, in today's session, we are going to discuss about the polar mount antenna and the limits of visibility, right? Now, the topics to be covered in the following session, that is first of all, examples of antenna look angles on which we have discussed in last session. Second, that is polar mount antenna, and third, that is limits of visibility. Now, first starting with the examples on antenna look angles. Here we have taken an example in which the question is like that: a geostationary satellite is located at 90° west, right? Calculate the azimuth angle and elevation angle for the earth station antenna at latitude this, that is 35° north, and longitude 100° west. Now, make sure that whenever you are calculating this examples on antenna look angles, make sure you will not change the denotions, which we have discussed in the theory. The same denotions you have to put it over here. So first of all, let's see the solutions. So first of all, what has been given? The geostationary satellite is located at 90° west. So for the geostationary satellite, 90° west. So what it is given? It is given as a longitude, right? So if it is given in east or west, that means a longitude. And only for geostationary orbit, it will be given as only a longitude. Latitude will not be given. Why? Because geostationary satellite did not cover the poles. Clear? So first, on the basis of that, the given quantities are, right? So, and the earth station having the two quantities, latitude 35° north and longitude 100° west. Now, make sure that whenever with the help of directions, you have to substitute negative and positive sign. So for longitude, if it is a east, then you have to write positive value for that. If it is a west, then you have to write negative value. Let's say here the earth station antenna has longitude 100° west. So earth station longitude, it is denoted by phi e, and that is equal to, it is as 100° west is given, so minus 100 degrees. Clear? Right? Now, similar, the satellite having a 90° west, so it will be represented by 90 minus 90°. And for latitude, if it is north direction, then it is taken as positive, and if it is a south direction, then it is taken as negative. So latitude, that is denoted by lambda e, that is equal to 35°, which is positive because it is a north. Yeah. So these three quantities will be given each and every time whenever you need to calculate an examples on antenna look angles. Now, the first step you need to calculate is calculate capital B, which is the difference between earth station and subsatellite, phi e minus phi ss. So what it will be? Minus 100 minus 10. So what it will be? It will be equal to minus 10, right? Minus 100 minus 90. So it will be equal to minus 10. Once you find this capital B, the second step is you need to find small b. So the formula for small b, which we have discussed in last session in the theory of antenna look angles, that is arc cos, which is nothing but cos inverse. Cos inverse, cos capital B, cos lambda e. Now see, cos capital B you have find out over here, and lambda e, it is already given in the question. So substitute both capital B and lambda e value here, take both cos product and then take the cos inverse. So you will get small b value, that is 36.23. Clear? Now, in the third step, you need to find capital A. So capital A, that is equal to arc sine the mode B divided by sine B. So again, sine B, capital B is we have find out, and small b also we have find out in the last step. So substitute this B and small b in the value this. Make sure here it is a modulus B. So you have to take positive 10. Clear? So substitute in this, take the division and take then sine inverse. So you will get capital A, which is equal to 17.1. Right? Now, based on this capital A value, we will find out azimuth angle. So azimuth angle will depend on which two values? So as we have discussed in the last session, the table 1, that is, it depends on lambda E and B. So here lambda E is positive and B is negative, right? So we will have a third condition. So based on third condition, AZ will be equal to 180 minus A, which is equal to 162.9. So the azimuth angle for that particular location, that will be equal to 160.9. Now, next we need to find out, that is elevation angle. So for elevation angle, first of all, we need to carry out D, small d, which is range. So for range, that is radius of Earth, that is given as 6371 kilometer, and radius of geostationary, which is AGSO, that is 42,164 kilometer. Again, this we have studied in the last session, that is height of geostationary. Clear? Now, from this is the equation of D which we have taken from the last session, which is R square plus AGSO square minus 2 into R into AGSO into cos small b. Small b we have taken value which we have calculated in previous time. So from this, substitute these values and calculate D, which is equal to 37,215 kilometers. Now, make sure that the D value will lie from 36,000 to 42,000, right? As it is a range that is from Earth station to satellite. Clear? So it will not be smaller than 36,000 kilometers. Clear? Right? Now, once you find a D, substitute in the equation EL, that is arc cos AGSO divided by D sine small b. So AGSO divided by D sine b. So what is the EL? That is 48-degree elevation. So here we have find out, that is azimuth angle and elevation angle for the antenna loop angles. Yeah. So this way you need to carry out the sums, right? And similar kind of examples can be practiced by you from the reference book discussed, which is given in the Dennis Lodi example session, right? Last session. Clear? Or you can go from the you can take the questions from TechMax, but make sure you calculate with these formulas only. Don't follow this topic from the TechMax repeat. Clear? The equations given in the TechMax are very complex. Now, next we are going to discuss, that is polar mount antenna. So, what is the, first of all, what is the need of polar mount antenna and what is polar mount? So, the antennas are pointing accurately only for one satellite, right? Now, when we talk about the geostationary satellites, it will have only one antenna which is pointing to only one satellite. They have single accudator, that is motion of antenna, right? So as they have single accudator, they will move only the antenna in a circular arc, which is press the which is when the satellite will move, right? So generally some pointing error is seen in this antenna. So these due to this errors seen in this antenna, what we have done is, the dish of antenna is mounted on an axis termed as polar axis, and such the antenna, that the antenna bore side, that is nothing but antenna gain, which is the maximum radiation pattern, right, is normal to the axis, which is seen in figure 1, right, which we discuss. Now, the angle between polar mount and local horizontal is set is equal to earth station latitude lambda e, making bore side lie parallel to the equatorial plane. Now, so the axis is tilted at angle S, which is relative to the polar mount until the bore side is pointing at satellite position. Now, see these figures. Now, first figure that we have discussed, that is this antenna is mounted at polar axis, right, of the earth station, right, and it is having the antenna bore side gain in the parallel to the equatorial plane. Clear? Now, this is the satellite point, right? Now, what it will do, these antenna in this the dish which we have mounted on the polar axis, this will rotate till which it is rotate till that the satellite point out its angle. Clear? So this angle, that is called as the angle which we have mounted, that is at the earth station latitude lambda e, right? And the mounting which we are doing, or we are tilting the angle, that is nothing but angle that is 90-degree, and the delta, that is the tilt angle, till this we are tilting this both side angle. Clear? So we will get here, that is D, that is from earth station to satellite, that is D range. Now see this triangle. So what you will find is, this is R, then this is D, so R, D, and here that is AGSO. So and now this is lambda e. So from this, this will be also equal to lambda e, alternate angles. So it will be equal to lambda e, right? And here this angle, right? Which angle we are talking about? So this, as this angle is 90, so here this angle will be also 90. So there is 90 plus EL0. Now based on this triangle, we will calculate the equations for and find out the tilt angle delta. So how we can find out? So delta tilt angle, that will be equal to 90 minus EL0 minus lambda e. How it can be calculated? So let's see. This is whole. This forms whole 180 degree. So 180 minus 90, that will be equal to 90. 90 minus lambda e minus EL0, that will be equal to nothing but delta. Clear? So here delta is equal to 90 degree minus EL0 minus lambda e. Now we need to find lambda e will be given, that is latitude of our station. We need to find out EL0. So EL0 can be find out with the help of equations which we have used in antenna loop angles, right? So EL0, that is elevation required for the satellite positions. So now what is EL0? So we have EL0, that is equal to cos inverse, right? So cos inverse, the cos inverse will come over here. The cos EL0, that is equal to AG also divided by D into sine lambda E. Here small b and lambda E, that both are same, right? As we have changed the molar mount into only one axis. Clear? So substitute EL0 equations from this into these main equations. You will find delta, that is equal to 90 degree minus arc cos AGSO by D into sine lambda E minus lambda E. Clear? So this, from this equation you will find the angle of tilt. Right? Now based on this equation we will see, or we will calculate one example. So for this, the example, the equations, the questions has been given like, determine the angle of tilt required for polar mount used with an earth station at latitude 49 degrees north. Assume that the earth spherical earth of mean radius, this means earth radius is given this, and ignore the earth station latitude, and latitude has been given 40 degree north, which is positive. So now let's see the solutions. So this is lambda e, which is north, so it is be taken as positive 49 degree. AGSO, which is constant for a 42,164. Radius of earth again constant, and here E and by lambda E, that is equal to 49. So first calculate D from the equations which we have discussed in antenna loop angles, which is R square plus AGSO square minus 2R into AGSO into cos B. Here B will be replaced by lambda E. Here, so you will find out D value, that is 38,287. Now as you will get the D, find EL. So EL, that is equal to arc cos AGSO divided by D into sine lambda E. So it will be equal to 33.8. Now the final, that is angle of tail, that is equal to 90 minus EL0. EL0, that is 33.8 minus lambda E, that is equal to 49. So calculating the calci, you will get the delta tilt angle, that is equal to 70. Clear? Now, next, that is limits of visibility. Now, first of all, what is the limits of visibility? So, as we are discussing about the Earth geostationary orbit, so there will be a limit of limits of visibility for the satellite from the center of Earth in the east and west direction. So there will be east and west limit on the geostationary arc visible from any given Earth station. These limits will be set by the geographic coordinates of the Earth station and the antenna elevations, right? So the lowest elevation in the theory is 0 when the antenna is pointing along the horizontal. As east and west are in horizontal, so the lowest elevation will be 0 when the antenna is in horizontal direction. Now, a quick estimate of longitudinal limits can be made by considering the Earth station at the equator with the antenna pointing either west or east along the horizontal, as shown in figure. So the limiting angle can be given by, so theta will be given by arc cos AE divided by AGS. So cos inverse AG by AGS. So substitute radius of Earth 67.8 and AGS of 42,164. The limits of visibility will be equal to 81.3 degree. Right? Now, as you can see in this figure, the Earth station is at the center of Earth, right? Here are the east and west visibilities. So from the center of Earth, this is the radius of Earth, and this is the radius of geostationary orbit. It makes 90-degree angle, right? So this will be equal to adjacent, so it will be equal to cos theta. So cos theta is equal to AE divided by AGS. So theta will be equal to cos inverse AG by AGS. Clear? So this way you can find out the limits of visibility. Now, thus, for this situation, an Earth station could see satellites over a geostationary arc bounded by 81.3 about the Earth station longitude. Clear? Right? So a maximum it is seen over 81.3 degree, plus or minus 81.3 degree, whether it depends on the east or west. In practice, to avoid reception of excessive noise from the earth, some finite minimum value of elevation is used, which is denoted by EL minimum, and it is taken as 5 degree compulsory. Clear? So the limits of visibility will also depend on the earth station latitude. Now, as we have discussed the planar triangle figure from antenna look angles, S will be represented by the angle subtended at a satellite where angle minimum that is equal to 90 degree plus EL minimum. Clear? So applying the sine rule, we will have S that is equal to arc sine R by AGSO sine delta minimum. But delta minimum, that sigma minimum, by sigma minimum is equal to 90 plus EL minimum. Clear? Now, a sufficient accurate estimate is obtained by assuming a spherical earth of radius this, which we have done previously. So, one S is known, angle B can be found. How can we find out? So, B is equal to 180 minus sigma minimum minus S from the planar triangle which we have done in polar bound antenna. And capital B from the equation of antenna look angles, which is cos inverse cos B by cos lambda E, right? And substitute both this. So the once B is found, the Earth station satellite longitude can be determined, that is phi E plus B when the satellite limit east of the Earth station, and when the west of Earth station, that is equal to phi E minus B. Clear? Now, based on this, we will see one example based on limits of visibility. So, determine the limits of visibility for an Earth station situated at mean sea level at this latitude, which is 48.42 degree north, and longitude 89.26 degree west. Assume minimum angle of elevation that is equal to 5 degree. So, latitude has been given, and longitude has also been given, that is 89.26 degree west, which is negative. So first of all, lambda that will be equal to 48.42 positive, which is north, and phi E, which is in west, so it will be a negative minus 89.26. EL minimum is 5, AGS and R we know that. So first of all, we will find sigma minimum, which is equal to 90 plus EL, right? So it will be equal to 95. Now this sigma minimum we will substitute in the equation of S. So arc sine, this is RE, that is radius of earth, divided by AGSO into sine sigma minimum. So it will be 8.66. Now, as we will get S, the next step we will substitute in the equation of small b. So we will have 180 minus 95 minus 8.66, which is equal to 76.34. And last, what we will do, we will substitute the value in capital small b, we will substitute in capital B to find out the capital B. So arc cos 76 is cos B by cos lambda I. So it will be equal to 69.50. Now, whenever we need to find the limit east of the Earth station, that will be equal to phi E plus B. What is the phi E? That is equal to minus 89.26 plus 69.15. So it will be minus 20 degree approx. And the west of the Earth station, phi E minus B, so minus 89 minus 69, that will be equal to minus 150 degree, minus 158 degree approx. Clear? Right? So in today's session, we have discussed the examples of antenna look angles and two more topics, that is polar mount antenna and limits of visibility, and we have seen the examples of each. Clear? So that's all for the today's session, right? Thank you.